Okay, in our lecture for today, we're going to start the Chapter 5 material on multiple integration. And in section 5.1, we'll talk about double integrals defined over rectangular regions. So throughout Chapter 5, what we're going to be doing is integrating functions of two or more variables over some domain or over some part of their domain. And to introduce the way that this is going to work, in section 5.1, we'll talk about the integral of a function of two variables, which would yield something called a double integral, where our domain, or the region that we're integrating over, is a rectangular region. So to introduce this concept, let's consider a function f of two variables, x and y, and it's defined on a closed rectangle, R, which would be the Cartesian product of the interval from a to b with the interval from c to d. So really what that means is we're looking at the set of all points in the real plane such that our x-coordinate lies between a and b, and our y-coordinate lies between c and d. So in my blank space below here, I'm going to sketch a little figure to illustrate what we're doing as we're working up to our definition of a double integral. So in the xy plane, we're working with some rectangle where our x interval is from a to b, and our y interval is from c to d. So here we're looking at a rectangle which would consist of the points where our x-coordinate is from a to b and our y-coordinate is from c to d. So this is going to be our rectangle R somewhere in the xy plane. And what we're going to do is partition our intervals a to b and c to d by choosing partition points in each interval. So my x interval, I'm going to choose a value of x naught as the left end point A, and x sub m as the right end point B, and I'm going to choose a lot of values of x in between those points. So some number x1, which is greater than x naught, x2, which would be greater than x1, and so on. So here below, in my rectangle, this left end point A is going to be x naught. Then I'm going to choose an x1, an x2, an x3, and so on, until I get to my right end point B, which is what I'm calling x sub m. So we're dividing up our x interval into these little subintervals, x naught to x1, x1 to x2, x2 to x3, and so on. And in a similar way, I'm going to partition my y interval from c to d by choosing some y value, y naught, as the lower y value for my interval, c. Then choose a point greater than that, y1, and then y2, which would be greater than that, and so on, until I get to my right end point, y sub n, which is equal to d. So along the y-axis, I've got some y naught, which is equal to c, and then I'm going to choose different y values, y1, y2, y3, and so on, until we get to our upper value for y, which we'll call y sub n. So this partition of my x and y intervals forms a partition which we'll denote as capital P of our rectangle into m times n subrectangles. So here the subrectangles will denote as r sub ij, which would be the rectangle whose x interval is from xi minus 1 to xi, and the y interval would be from yj minus 1 to y sub j. So this partition of our x and y intervals gives us a partition of my rectangle in the x direction and a partition of my rectangle in the y direction. So we're dividing up our large rectangle R into these little sub-rectangles. Say R11, R12, R13, R21, R22, and so on. So altogether, if we had a partition with m different values for x and n different values for y, we have m times n subrectangles. And the width of each of these rectangles will denote as delta x sub I. So the width along the base of this first rectangle would be delta x1. For the second one, delta x2. For the third one, delta x3, and so on. And the height of these rectangles will denote as delta y sub j. So for the height of our first rectangle, we have delta y1, delta y2, and so on. So the area, then, of the rectangle R sub ij is denoted as delta of A sub ij, and it would be the product of the length and width of these rectangles, or their width and height. Now, once we have the area of our ijth rectangle, we're going to choose some representative point. Let's denote our point as x sub ij star, y sub ij star in the rectangle R sub ij. So within each of these rectangles, we're going to choose some representative point. Could be a different location of point within each of our different rectangles in our partition. And once we choose a representative point in each of our subrectangles, we're going to form what's called a double Riemann sum. So here our double Riemann sum will be evaluated as follows. So we're going to take the value of our function f that we're working with at the ijth representative point. So for each of these points that we chose in our rectangle, we're going to evaluate our function at that point and then multiply by the area of the rectangle where we chose that point. And then we're going to add up the values of our function times the area of this rectangle over all such rectangles. We take the double sum as I and j go from 1 to m or from 1 to n. So we're adding up along all our x partition values and our y partition values. Now, once we have this double Riemann sum, we're going to let this norm of p denote the norm of our partition, capital P, and we're going to define it as the length of the longest diagonal of all of my subrectangles. So whatever our partition is, the norm of our partition is going to be the longest length along any rectangle in our partition. And we're going to be interested in letting the norm of our partition approach 0. So notice if the length of the diagonal for our longest rectangle is shrinking down to 0, then our partition of our rectangle becomes finer. We're dividing it up into smaller and smaller subrectangles. So finally, we can define what is called a double integral of our function through this process. We would say the double integral of the function f over that rectangle R is the following. It's denoted by using two integral symbols with a subscript below them of R, defining our rectangle, of the function f of two variables, x and y, times the differential of A. Here, the differential of area is what this represents. And this will be defined as the limiting value of that double Riemann sum as the norm of our partition P approaches 0, as long as that limit exists. Now, if this limit does exist, then the function f is called integrable. It's said to be an integrable function over that rectangle. Now that we have defined a double integral of a function in terms of the limit of a double Riemann sum, let's look at some examples. So, to define a double integral formally in terms of a double, or the limit of a double Riemann sum, is pretty tedious. It's quite difficult. So instead, we could approximate the value of a double integral over a rectangle by looking at a double Riemann sum, but not taking the limit as the norm of our partition approaches 0. So in this next example, we'll consider that sort of approximation. Here we are asked to find the approximate value of the double integral of x squared plus 4y over the rectangle R given by 0, 2 cross 0, 3. And we're approximating by computing a double Riemann sum using the partition lines x equal 1, y equal 1, and y equal 2, and taking our representative points to be the upper right corner of our rectangles. All right. So we'll show a little bit later in this section that we can actually evaluate the value of this double integral. It works out to be 44. We'll see how to find that a little bit later in this section. But let's see if we could approximate our value by using a double Riemann sum. So for these problems, I usually like to start by visualizing the rectangle that we're working with. So in this example, we have the rectangle where in the x direction, we are going from 0 to 2, and in the y direction, we're going from 0 to 3. So we have the following rectangle R, and we're told that we were using the partition lines at x equal 1. So we'll divide our rectangle using the partition line at x equal 1, and then the lines y equal 1 and y equal 2. So here we get the following subrectangles, not drawn to scale here. And we're supposed to form the double Riemann sum by taking our partition, or taking our representative point to be the upper right corner of our rectangle. So in each of these rectangles, we're going to take the upper right corner of our rectangle as our representative point. So in order to approximate this double integral, that is the double integral over the rectangle R of x squared plus 4y dA, we can make use of a double Riemann sum. So this value is approximated by the double sum where I ranges from 1 to 2, and j ranges from 1 to 3, I and j being the number of subdivisions I had in the x or y direction. And we're evaluating for this Riemann sum our function f at the point xij star, yij star, so at our representative point, and we multiply by the differential of delta a sub ij, which would be the area of our ijth rectangle. Now we see from the partition that we're using here, for each of these rectangles, R11, R12, R21, R22, R31, or R33, that we would have our area as equal to 1, because the length and width, or the base and height of each of these rectangles, is 1. So when we're forming this double Riemann sum, for our first representative point, we will have the value of our function at this upper right corner point, which was 1, 1, times the aij area, which is 1. Plus the value of our function at the next representative point, which would be 2, 1, times the area of that rectangle, which is 1, plus the value of our function at the point 1, 2, times the area of that rectangle, which is 1, plus the value of our function at the point 2, 2, times the area of that rectangle, which is again 1, plus the value of our function f at 1, 3, times the area of that rectangle, plus the value of our function at the last representative point 2, 3, times the area of that rectangle, which was 1. So here, if we evaluate our function at the point 1, 1, we have a value of 5 times 1, plus the value of our function at 2, 1 is 8, plus the value of our function at 1, 2, which is 9, plus the value of our function at 2, 2, which is 12, plus the value at 1, 3, which is 13, and then plus the value of our function at 2, 3, which is 16. So here altogether we're left with 63, and we said above the true value is 44, so this is not a very good approximation in this case. So let's look at another part of this example. In part B, we are asked to use the same rectangle, but where our representative points are now taken as the center point of the ijth rectangle. So here, let's start again by visualizing the rectangle that we're working on, which is the rectangle from 0 to 2 in the x direction, 0 to 3 in the y direction. And we're partitioning that rectangle using the lines x equal 1 and the y lines y equal 1 and y equal 2. And in this case, we're taking our representative points to be the centers of each of these rectangles. So we have the following. Now again, we're using the same partition for this example. So the area of our ijth rectangle is still 1. We're just changing what representative points we're taking. So here, the double integral of r, or over r, of x squared plus 4y dA is approximated by the double Riemann sum, where I goes from 1 to 2, j goes from 1 to 3, of f of x ij star y ij star times delta a sub ij. Now, this last value is 1, so we just have the value of our function f at these representative points added together. So here, we would have the value of f at our first representative point. Now, taking the center of that first rectangle, we have 1/2, 1/2, plus f of, at our second rectangle, we have its center as 3/2, 1/2, plus the value of the function at the next representative point, which would be 1/2, 3/2, plus the value of f at the next point, 3/2, 3/2, plus the value of our function at the next point, 1/2, 5/2, plus the value of our function f at that last representative point, 3/2, 5/2. So evaluating our function at these points, we are left with, for our first value, 9/4 plus 25/4 plus 41/4 plus 17/4 plus 33/4, and lastly plus 49/4. So altogether, this leaves us with 87/2 in simplified form, which is 43.5. We get a much better approximation in this case if we used the midpoint of our rectangles as the representative point. Now, this case where we're approximating our double integral by choosing our representative points to be the centers of our rectangles, this process for our approximation is called the midpoint rule for double integrals, the approximation where we're using the midpoint or the center of our rectangle. So let's look at another example of approximating these double integrals making use of a Riemann sum, and see how we can interpret a double integral geometrically. So we recall that a single integral, in particular a definite integral, of a positive function can be interpreted as area under a curve. Now, in a similar way, we can interpret double integrals of positive functions in terms of the volume that lies under the graph of our function and above a rectangle. So to make that a little more precise, let's look at the following theorem, which is a theorem explaining the volume related to a double integral. So if we have a function f of two variables, which is non-negative, and it is continuous on the rectangle R, then the volume, V, of the solid region that lies above the rectangle R and below the surface, which would be the graph of our function, is given by the double integral of our function over that rectangle. So just like a single integral represents area under the graph of a function over some x interval, a double integral represents volume under a surface and above our rectangle. So now that we have this interpretation as volume, let's look at the following problem, where we are asked to estimate the volume of the solid region that lies below the surface z equals x times y, and above the rectangle R, defined as 612 cross 48, and we're going to approximate this by evaluating a double Riemann sum, where m is 3, so that is we're dividing our x interval into 3 subintervals, and n is equal to 2, so we're dividing our y interval into 2 subintervals and making use of the midpoint rule. So as we saw in our earlier example, my first step here might be to visualize the rectangle that we're working with. So here, our rectangle R is the rectangle where in the x direction we're moving from 6 to 12, and in the y direction we're moving from 4 to 8. Now, we were told that we're using a double Riemann sum where m is equal to 3. So in our x direction, we're going to divide our interval up into 3 subintervals. So to get the width of the x intervals, we're going to take the length of our x interval, which is 12 minus 6, and divide it equally into 3 pieces. So we get delta x is 2. So our partition lines are going to be moving 2 units to the right of 6, we would have 8. Moving another 2 units to the right, we have 10, and then at 12. So we're partitioning in the x direction with the lines 8 and 10. And in the y direction, delta y, the width of our, or the height of our rectangles, is going to be taken as the length of our y interval, 8 minus 4, and dividing equally into 2 subintervals, since n was 2. So here we get 2 for the height of our rectangles. So we're going from 4 up to 6, and then from 6 to 8. So we've got the following sub-rectangles, and we're supposed to be using the midpoint rule. So we're going to choose the centers for each of these rectangles as our representative points. So this volume that I'm interested in approximating is given by the double integral over the rectangle R of the function z, which is x times y, dA. And we can approximate this as a double Riemann sum, where I ranges from 1 to 2, j ranges from 1 to 3, of the value of our function f at the ijth representative point, times the area of the ijth rectangle. Now here we can see that the area of each of these rectangles is going to be a constant value, 2 by 2, or 4 units. So this constant 4 for the area that I have on the end, I can pull out in front of my double Riemann sum, which leaves us with 4 times the value of our function at each of these representative points added up over each rectangle. So for this first rectangle, our center point is the point 7, 5. For the second one, our point is 9, 5. For the third one, we have 11, 5. For our fourth one, we have 7, 7. For the fifth one, we have the point 9, 7. And for our last one, 11, 7. So our function, f in this case, was just the product of x times y. So at our first point, we have 35, then plus 45, plus 55, plus 7 times 7, we've got 49, plus 9 times 7 is 63, and then 11 times 7 is 77. So altogether, this leaves us with 4 times 324, which leaves us with 1296 for the approximate volume of that solid. Now in this next example, we are asked to evaluate a double integral exactly over some rectangle by identifying it as the volume of a known solid. So here, the double integral that we're working with is the integral of 4 minus 2y over the rectangle 0, 1 cross 0, 1. And we're supposed to evaluate this exactly. So let's see if we could sketch our surface and think about the volume that lies underneath that surface but above our rectangle, and see if we could find that volume. So here I'm working in space. So let me start by sketching my coordinate axes. Here we've got our x, y, and z axis. And the rectangle that I'm integrating over is 0, 1 cross 0, 1. So in the x direction, we're going out at most 1 unit. In our y direction, we're going out at most 1 unit. And our rectangle R is the following rectangle shown in the xy plane. Now the function that we're given here is the function 4 minus 2y. So if we think about the surface, z equals 4 minus 2y, this defines a plane. And let's visualize what this the part of this plane looks like that lies above our rectangle, 0, 1 cross 0, 1. So I know here at the origin, when x and y are both 0, the value of z is going to be 4. So at 0, 0, my z value for the function would be 4. And if I move out in the x direction 1 unit to the point 1, 0, if x is equal to 1 and y is equal to 0, we would also have a y value of 4. So along this edge of our rectangle, where y is equal to 0, our z value is always going to be a constant 4. Now, as y increases towards 1, our z value will decrease. So let's look at the value at this point, 0, 1. When x is 0 and y is 1, we have a value of our function of 2. So we're 2 units above that point 0, 1. And everywhere along this line segment from 0, 0 to 0, 1, my x-coordinate is 0. So we're moving from this point to this point as y increases. My value of z is decreasing from 4 to 2. Now, similarly, at this point 1, 1, the value of our function is also 2. And everywhere along this edge of our rectangle, where y is defined as 1, our z value will have a constant value of 2. So we're moving along in this direction. Now along this last edge of our rectangle, from 1, 0 to 1, 1, our x value is a constant 1, y is increasing from 0 to 1, so our z value is decreasing from 4 to 2. So the solid region that we're describing the volume of would be the solid region that lies above our rectangle, 0, 1, cross 0, 1, and below that plane. Now, to find the volume of that solid, and therefore the value of this double integral, we could think about splitting this solid up into 2 pieces. So if I think about slicing this solid up into a couple of pieces, well, I can think about it as consisting of 2 parts. Our volume, which is this double integral, can be thought of as the sum of the volumes of these 2 pieces of my solid. So here, the first part of my solid is going to be this rectangular prism that lies below the plane z equals 2 and above my rectangle. So the volume of that first piece, V1, is going to be the area of the base of my rectangular prism. So since our rectangle was 0, 1 cross 0, 1, we have a base area of 1, and then the height of this was 2, the value of our function at, say, 1, 0, or at 0, 0, rather. So we get a volume of 2 cubic units for that first part of our solid. And then we're also looking at the area that lies underneath the graph of our, or the volume that lies underneath the surface and above this rectangular prism. So here we have this little wedge, or half of a rectangular prism, whose volume would be half of the volume of that red rectangular prism. So we get plus a value of 1. So altogether, this double integral, v, is 3. So here we were able to calculate the true value of this double integral without making use of a double Riemann sum by thinking about the volume that it represents. And here, by visualizing the graph of our function, we see that we get a solid region whose volume can be computed using a geometric technique. Now, we can't always